This second lecture will also be part of our preliminaries before we start studying groups in abstract algebra. Lecture 2, Relations and Functions. We'll define a relation. Let S be a set. A relation, R, on S, is a subset of S cross S, that is the Cartesian product of S with itself. If the ordered pair AB is in that subset R, then we can write A squiggle B, or you may see it as also written as ARB. ARB. So R can be used to symbolize the relation, and it also is the name of the subset. And the relation actually is a subset of S cross S. So let's review what we mean by a Cartesian product. If A and B are two sets, the Cartesian product of A and B is the set of all ordered pairs A, B, such that the first element of the ordered pair comes from A, and the second coordinate comes from B. So let me give you an example. Let's say that A is the set containing 1, 2, and 3. Then A cross A is this set of 9 ordered pairs that I wrote here. All ordered pairs where the first coordinate comes from A and the second coordinate comes from A. Now, what about this subset? Let's call R the following subset of A cross A. In other words, we're going to define R as a relation on the set A. So let's see, how about the ordered pair 1, 2, and the ordered pair 1, 3, and the ordered pair 2, 3. Now that subset of A cross A is a relation on A. And we can say that 1 is related to 2, 1 is related to 3, and 2 is related to 3 in this relation. And actually what I was thinking is that A is related to B if A is less than B. So this is a relation defined on the set A equals the set containing 1, 2, and 3. Any subset of the Cartesian product is a relation. For example, we don't need sets of numbers. If S is the set of people in our class, define a relation on S by, well, A is related to B, one person is related to another, if A and B are the same age. This relation has some special properties, and so I'm going to write down the 3 properties that this has, and then we will give a formal definition in the next slide. First of all, A is related to A for all A in S. In other words, each person is the same age as his or herself. 2, if A is related to B, then B is related to A. If A is related to B, B is related to A. If one person is the same age as another, then certainly you could reverse that statement. 3, if A is related to B and B is related to C, then A is related to C. And it's obvious, if A is the same age as person B, and person B is the same age as C, then A and C are also the same age. A relation that satisfies those 3 properties is called an equivalence relation. Equivalence relation. If you look at the relation that we first spoke about, the subset of A cross A, containing just 3 ordered pairs, notice each element is not related to itself. 1, 1 is not there, 2, 2 is not there, 3, 3 is not there. And also, if A is less than B, then B is not less than A. So number 2 does not hold. And number 3, if A is related to B and B is related to C, well, then A is related. If A is less than B and B is less than C, then A is less than C. But this is the only property of the 3 that the first relation we gave satisfies. But the second one is called an equivalence relation. There's another interesting thing to notice about equivalence relations. If I drew like a diagram here, let's just make a rectangle, and I say that all 35 people in our class is inside that rectangle, then we could say, well, some of you are 18 years old, and so we could say the 18-year-olds are here, and maybe most of you might be 19 years old, and then there's maybe some are 20-year-olds, all of them in here, and then there's one person, me, who belongs in a different spot, because I'm not 18, 19, or 20. But notice that the whole class is subdivided into what we call equivalence classes. The whole set is there, and it is divided into 4 subsets called equivalence classes. And the union of those subsets is the entire class, and the intersection between any of those subsets, any 2 of them, is empty. So we'll talk about this in greater detail, but equivalence classes are important. An equivalence relation on S is a relation, in other words, it's a subset of S cross S, squiggle I'll call it, satisfying 3 properties. 1, A squiggle A, for all A in S. It is called the reflexive property. Number 2, if A is related to B, then B is related to A, the symmetric property. And 3, if A is related to B and B related to C, then A is related to C, the transitive property. If these 3 properties hold, then the relation is called an equivalence relation. Let's look at some examples. Number 1, let's define a relation, squiggle, on Z, the integers, as follows. A is related to B if A is congruent to B mod 4. So let's test all 3 properties. Well, we know that this is a reflexive relation because, of course, A is congruent to A mod 4 for any integer A. So we have the reflexive property. If A is congruent to B mod 4, that implies that B is congruent to A mod 4. Obviously, here 4 divides A minus B, so 4 divides B minus A. So that's what, remember, that means. If A is congruent to B mod 4, 4 divides their difference. And now, so we have the symmetric property. And if A is congruent to B mod 4, and B is congruent to C mod 4, we want to know, is A congruent to C? Well, it is, but let's prove it. If A is congruent to B mod 4, that means that 4 divides A minus B, and since B is congruent to C mod 4, 4 divides B minus C. Well, what does it mean to divide? It means that A minus B is equal to 4 times some integer n, and b minus c is equal to 4 times some integer m. So let's see, we want to look at, we're hoping to see if a is related to c. So let's just add these together. A minus b plus b minus c is equal to 4n plus 4m. Now if we take the parentheses off, you see that the b's cancel, and we have a minus c is equal to, and factoring out the 4, we have a minus c is equal to 4 times an integer n plus m. So this implies that a is congruent to c mod 4, and we have the transitive property. So the relation is an equivalence relation. So watch how this relation, congruence relation, partitions the set of integers into equivalence classes. So I'm just going to draw an oval here that represents all of the integers. Now we have a whole bunch of them that are related to 0. So let's just use that notation, square brackets 0, to represent all of the integers that are equivalent to 0. And we'll have another part of this, the integers blocked off here for all of the integers equivalent to 1 mod 4. And we need all of the integers equivalent to 2 and all of the integers equivalent to 3. Now every integer will fall into one of those subsets, won't they? For example, in the first, in square bracket 0, we'll have -4, and let me switch colors. We'd have -4, we'd have -8, we'd have -100, we'd have 0 and 4 and 8 and 12, etc. We'd have all of the numbers, all of the multiples of 4 would live in there. Now in the equivalence class represented by the number 1, well, we would have all of the numbers where if you take 1 away, it's divisible by 4. So in other words, we'd have minus 3, and we'd have -7, and we'd have 1 and 5, and we'd have 9, we'd have 101. All of the numbers that if you subtract 1, it is divisible by 4. Or in other words, if you divide by 4, you have a remainder of 1. Here we'd have in square bracket 2, or the equivalence class represented by 2, we would have all of the numbers that leave a remainder of 2 when divided by 4. So we would have -2, we'd have 6, we'd have 10, we'd have 2, and we'd have -6. All of those numbers when divided by 4. Using the remainder theorem, you would get a remainder of 2. And likewise over here in the equivalence class represented by 3, we would have, well, of course, 3, and then we would have 7 and 11, and we'd have -1, -5, etc. And this has broken up, it has forced a partition of the set Z. None of those equivalence classes have anything in common. The intersection, the pairwise intersection, is the empty set, and if we take the union of all of them, we have the entire set of integers. So let's look at the relation less than or equal to defined on the set of integers. Now, we don't write it as such, but remember it's a subset of Z cross Z, where every ordered pair in that subset has first coordinate less than or equal to second coordinate. But we can check for the 3 properties and see if it is an equivalence relation. Well, first of all, we want to ask ourselves, is A less than or equal to A for all A in Z. And of course that's true. So we do have the reflexive property. If A is less than or equal to B, though, it does not mean that B is less than or equal to A. So we do not have the symmetric property, and we know that we do have the transitive property. If A is less than or equal to B, and B is less than or equal to C, then A is less than or equal to C. So we have the transitive property, but this is not an equivalence relation. And as such, it will not divide Z into equivalence classes that are pairwise disjoint, and the union of which is all of Z. I've been using the word partition, so let's define what we mean by that formally. A partition of a set S is a collection of mutually exclusive, meaning pairwise disjoint, meaning that if you take any pair of them and intersect, the intersection is empty. Pairwise disjoint subsets of S whose union is all of S. So there's two properties of a partition. They are pairwise disjoint sets whose union is all of S. Let's call it squiggle. Let squiggle be an equivalence relation on S. The equivalence class of A is denoted by square bracket A, and it is the set of all X in S such that A is related to X. So the equivalence class of A is the set of all other elements in S that are related to it by squiggle, whatever relation it is. So we can't go through a lecture without at least one proof. Let's prove that the equivalence classes induced by an equivalence relation squiggle form a partition of S. So there's a lot for you to learn in this proof. One, be sure and look at the notation that I use, and I'm going to, in red, write some little notes for you how to prove things. So we begin by saying, well, we want to prove that the equivalence classes induced by squiggle form a partition of S. So we must show that the union is all of S, and that any two of the equivalence classes that are not equal, in fact, have nothing in common. First, since A is in its own equivalence class, we know squiggle is reflexive. Since squiggle is reflexive, we know that every A is in its own equivalence class. So since every element of S is in its own equivalence class, certainly if we take the union of all of the equivalence classes, A in S, the union over all A in S of the equivalence classes of A, this is going to be equal to the set S. So we know that since the relation is reflexive, the union of the equivalence classes is equal to the set. Now, to prove that the equivalence classes are mutually exclusive, we have to show that here's what we need, if the equivalence class of A intersect the equivalence class of B isn't empty, then They are equal. The equivalence class of A is equal to the equivalence class of B. That's what we need to show in order to show that the equivalence classes are pairwise disjoint. So what I'm writing in red is you should include in a set of notes, maybe on a separate page, how to prove things. If you're going to prove that two sets are equal, you must show that one is a subset of the other, and vice versa. So if you want to show sets A and B are equal, show that A is a subset of B and B is a subset of A. Well, how do you prove that A is a subset of B? Let X be in A and show that X is in B. So in this case, we want to show that if two equivalence classes, those are sets, are not empty, their intersection is not empty, then they must be equal. So we're going to assume that the intersection is not empty. And we would do that by letting something be, supposing that there's an element in both of them. So suppose we have C in the intersection of two equivalence classes. That's what it means to not be empty. That means you could actually pick something in there. And then we want to suppose that's true, and then we want to set out to show that the equivalence class of A is a subset of the equivalence class of B, and that the equivalence class of B is a subset of the equivalence class of A. And that will tell us that the two sets are equal. Well, let C be in there. So the first thing, if I want to show them equal, I have to say let X be in the equivalence class of A, and I want to show that X is then in the equivalence class of B. Well, if X is in the equivalence class of A, then we know that X is related to A. We want it to be related to B. But we also know that C is in both of those equivalence classes. So X is related to A, and A is related to C. So let's try to use our transitive property here. We can get at least X is related to C. Well, that doesn't put it automatically into the equivalence class of B, but X is related to C, and C is related to B because C was in the intersection. So this does give us X related to B by the transitive property. Therefore, X is an element of the equivalence class of B, and we can conclude, therefore, that the equivalence class of A is a subset of the equivalence class of B. Notice I followed exactly what I had in red. I wanted to show that two sets are equal, so I have now proven that the equivalence class of A is a subset of B. And you should be able to fill in, do on your own. I'll just put likewise. You should try to make sure that you could prove it. The equivalence class of B is a subset of the equivalence class of A by following exactly the same logic. Therefore, we can conclude that the equivalence class of A is equal to the equivalence class of B. Notice what we have shown, that if the intersection is non-empty, in other words, we said, suppose there's something in the intersection, we have proven that if there's anything in there, that the two equivalence classes are exactly the same. This means that they are pairwise disjoint. The next topic we study is functions, and we're going to think of them a bit more abstractly as mappings from one set to another. A function can be viewed as a mapping from set A to set B, and this is the way that we say it. F colon A arrow B means that F is a mapping from A to B, and it is a rule that assigns to each X in A exactly one element in B. So A is obviously its domain. We can draw a picture to symbolize this. Instead of an X and a Y axis, our mappings won't necessarily be from the real numbers to the real numbers. There'll be a set A, a set B, and we'll indicate the arrow to be the mapping, the rule. So to each X in A, we map it to a Y, or we could call it F of X in B. Now let's just go through some vocabulary. Let's do X. X is called, X is the pre-image of Y under F, under the function. And Y is the image of X under F. We can think of F of the set A. Now this is not the rule applied to a set. The rule is applied to the elements of A. F of A actually is a subset of B. It might be all of B. But F of A is called the image of A under F. So it's a set. It's a different use of that notation. It's the elements of B that get hit by the mapping. For example, if F is a mapping taking the real numbers to the real numbers by, and here's the rule, F of X equals X squared, then this notation here, F of capital R, it's the range of the function. F of R would be equal to, the set of all positive or zero, so let's just say non-negative real numbers. So it's a subset of R. Likewise, if we said F maps the real numbers to the real numbers by F of X is the greatest integer function, the greatest integer less than or equal to X, well then F of R would be equal to just the integers, a subset of R. A function F is called a one-to-one mapping if, well, first let me just draw a picture. We have a set A and a mapping to set B. We can't have, a function could map two different x's to the same y. For example, f of x equals x squared. But not in a one-to-one. This cannot happen. Can't happen. A one-to-one function maps, if f of x1, let's say this were x1 and this were x2, if f of x1 is equal to f of x2, it must mean that x1 is equal to x2. In other words, one element in A is assigned to one element in B, and one element in B is hit by one element in in A, excuse me. So in red here are two important techniques of proof. You should add them to your list of how to prove things. If you want to prove that a mapping or a function is not one-to-one, you have to just provide an example. I'll show you an instance of that. Let's let f map the real numbers to the real numbers by f of x is equal to x to the fourth, let's say. It's a mapping, it's a function. Each x gets mapped to one y. But f of 1 is equal to 1, and f of negative 1 is equal to 1. Therefore, f is not a one-to-one function. You just have to provide one instance to show that different x's can map to the same y. Now, to prove that a function is one-to-one is a little more difficult. You have to suppose that f of x1 is equal to f of x2. That's always the first statement. And then you have to show by properties of the function that x1 must be equal to x2. Give you an example of that. If g takes the real numbers, maps the real numbers to the real numbers by g of x is equal to x cubed, then, well, you know that is a one-to-one function. If you think of the graph of y equals x cubed, it's always increasing. It's one-to-one. But how we show it algebraically is, suppose g of x1 is equal to g of x2. Then x1 cubed is equal to x2 cubed. And we know that we can take the cube root of both sides. This implies that x1 is equal to x2. We can conclude, therefore, g is one-to-one. These two proof techniques are what you use in real analysis, in algebra. Anytime that you want to prove that a function is one-to-one, you suppose that f of x1 equals f of x2, and you prove by using whatever the givens are in your problem that x1 is equal to x2. You may recall from calculus or pre-calc that when a function is one-to-one, it has an inverse. So it's a very important property of functions. Another property that a function may or may not have is being an onto mapping. If f is a mapping from A to B, if it's an onto, it is onto if for every y in B there is an x in A, such that f of x is equal to y. So let's draw a picture again. A and B, and we want, in order to be onto, we have to be able to pick any y in B and find an x in A that maps to it, f of x. In other words, all of B is hit by the mapping. In other words, f of A, that subset of B, is all of B. That's an onto mapping. So to show that a function is not one-to-one, you just have to give an example of a y in B that has no pre-image. For example, if f of x, again taking r to r, if f of x is equal to x squared, where f is taking r to r, f of x equals x squared is not onto, because there is no x in R with x squared, or let's just write with f of x being equal to -1, for example. None of the negative real numbers have pre-images, so f of r is not all of r. Now to show that a function is one-to-one, let me make up, let's say g of x, or g maps r to r by g of x equals x plus 1. That is going to be onto. G is onto. I want to prove it's onto. So you always do the same thing, no matter what class you're in, and no matter how high a level. You want to show that a function is onto, you let y be in the second set, in this case R, and we want to find an x. Well, g of y minus 1 is equal to y minus 1 plus 1. So we let y be any element in the second set. It's arbitrary. Let's write that down in parentheses. When you say let y be in R, what you're saying is really that y could be any element of R. It's arbitrary. And no matter what it is, y minus 1 is back in the first set, and G maps y minus 1 to y. So once you show that, you can say, therefore, G is onto. G is an onto mapping. Function composition is something I know that you have a good knowledge of, but let's draw a picture this way and think of it as a mapping. Well, we need three sets, A, B, and C. This is A, B, and C. And F is a mapping from A to B. And G is a mapping from B to C. So G circle F, G composed with F. G circle F maps A to C. G circle F, G composed with F is another mapping. And it is defined by G composed with F of X is G of F of X. And let me just mention something now that you probably don't see much of in other classes. Usually authors are careful to write G circle F or G composed with F. But in algebra, we're just going to write GF. It does not mean multiplication. In all of our algebraic structures that we look at, where the elements are actually functions, the only operation that we're going to use is function composition. So you think of GF as not G times F as it would be in a calc class. It is G circle F, and that will just be for this semester. GF means apply F first. You have an X in A, and then you get F of X in B, and then G picks up F of X. G is the second function to be applied, and you get G of F of X. I know you've all seen this before, and you know that G circle F is not necessarily the same as F circle G. In most cases, it isn't. There are four properties of functions that our author mentions in the text, and we're going to prove this first one, and you can just remember it. You can use it all the time. You will use this many, many times in our course, that function composition is associative. So in order to prove that, we need three functions. So let's let alpha map A to B, beta map B to C, and gamma be a function mapping C to D. And we want to prove that function composition is associative. Remember, it does not mean multiplication. So it's a very simple proof, and just watch how I do it, because you have to be so careful. The first one, we're taking alpha, beta, gamma. So apply gamma first, and then alpha, beta. All right, so let's put an X in. And, if you want to show two functions are the same, you have to show that they produce the same result. So alpha, beta, gamma is a mapping from A to D, and so is alpha of beta, gamma, or alpha this right here, applying beta, gamma first and then alpha. It doesn't matter which we apply first. So this would be alpha beta of gamma of x, which is alpha of beta of gamma of x. Let's do it the other way. If we first apply beta gamma, then this is alpha of beta gamma of x, which is now, what is that? Well, that is beta of gamma of x. This proof, honestly, it's hard for you to see that there's any difference in line 1 and line 2. Just remember that function composition is always associative. These other 3 properties of functions we are going to work on in class together. I'll ask you to prove these last 3 properties.